Yeah, so welcome to my talk, Get Ready to Rustle. If you wonder what that's supposed to mean, I have no idea really. I was just looking for something that included the word Rust, and then I thought I would just use that as a working title and change it later, but of course, change it later is just a different way of saying keep it forever. So, but this talk is about Rust, right? And the title is just something that mentions Rust. My name is Marco Otte-Witte. I'm founder and managing director of Main Matter. We are a consultancy. We build digital products for international clients. And we advise and mentor teams that develop their own digital products, right? And we help them sort of to overcome obstacles, adopt new technologies, ship better results faster, more reliably, and so on. And last year we made a strategic bet on Rust, right? Our goal is to help more teams adopt Rust and get access to all of the great benefits it provides. And we do workshops and mentoring, team augmentation, as well as custom development. If you're excited about Rust but don't know how to start, then feel free to reach out later, of course. And we're not the only ones who love Rust, right? Rust was voted the most loved language in the 2022 Stack Overflow survey, and so it was in 2021, as well as in 2020 and 2019, 2018, 2017, 2016, and there was maybe the first one anyway. So really, Rust is drowning in love, right? And there's probably some people here who love Rust as well. And it's not just the people here and the people on Stack Overflow, but it's also their management, right? At the big companies who love Rust. All of the big players in the industry are in the process, or some of them are well into the process already of adopting Rust, right? In quite significant ways also. AWS uses it heavily for their platform, right? They have the Firecracker stuff that I think runs EC2 or Lambda or something. So like all of the foundational parts of their services are in Rust or moving to Rust. Then we have Microsoft, who use it in Windows. It's used in Linux now. Google uses it for Android, and it flies planes and satellites. Because it's used in lots of embedded scenarios as well. So essentially, Rust is replacing C and C++ everywhere those were used before, right? Systems programming, operating systems, all kinds of embedded systems, low-level tooling, as well as games and game engines. I want to look at a slightly different area today, though, because I don't really know too much about these things neither, which is the web, right? And by web, I mean server-side, right? I'm not talking about like WebAssembly in the browser where you can use Rust as well, but I'm talking about like essentially backends, right? Anything that speaks HTTP or similar protocols. And the web is not really an area where many teams use C and C++ before, right? So so Rust might not be an obvious choice here for many teams. Yet we think Rust has a lot of potential in that area, actually, as it gives teams that build web and cloud apps access to capabilities that were previously out of reach, essentially, right? And what those capabilities are, we'll see more in detail later. I want to talk about the what, the why, the how and where of Rust on the web, and finally, look at where Rust on the web is going, right? So let's start with the what. What are we even talking about here? And what is Rust and what are its key characteristics, right? So welcome to the 5-minute intro to Rust, which is not actually 5 minutes long, as my team told me when I practiced. So I think it's a bit longer, but also you need to see everything. So Rust tagline is language empowering everyone to build reliable and efficient software. And I think the word empowering really is central here. Rust really is empowering large parts of our industry to achieve reliability and efficiency, in particular, at a level that was previously out of reach, as I said before, right? So let's see how Rust does that. First of all, we have to start with the bad news. 4 spaces for indentation is the default in Rust. I know the correct number of indentation is 2 spaces, but this is sort of a bitter pill that we have to swallow when working with Rust. Everything else is actually good. So let's start with the basics. Rust is strongly and statically typed, and it infers types when possible, right? You here see, you see X is not typed, but Rust infers the type, and Y is explicitly typed here. Unlike in many other languages, variables are immutable by default. So trying to change a variable here after it has been assigned a value, like in this example, results in compiler error. And by the way, as you can see here, Rust has pretty good error messages, right? They're typically well written and almost always suggest a way to fix the error that will also actually work, right? So while variables are immutable by default, there's opt-in mutability as well, right? This example compiles fine since X is explicitly marked as mutable here. Also, unlike many other languages, there's no concept of null in Rust. The only similar concept to null or nil or whatever it's called in the language is the union type, which represents the absence of a value. The union type itself is a real type though, right? So it cannot be assigned to anything that's of a different type, which means there's no notion of nullability in Rust. So here we said Y, which is of type usize, right, with numbers that's sort of as big as yeah, whatever. Like, it's a number type, right? And we're trying to set it to the value of X, but X is of the union type. So what happens is, because there's no concept of nullability, here we get a compile error, right? So while in languages like Java and others, any reference type could also be null, right? And you only know at runtime which one it is, right? The reference type or null. In Rust, a value is either of the union type or of another type, right? But those types are not compatible, right? And you know build time which one it is, and you get a compiler error where you would get a null pointer exception in a language like Java, for example. Besides the regular number, floating point, character, and so on types, Rust also has a bunch of compound types. So, for example, there's tuples, which represent collections of values of different types. There's fixed length arrays, and there's also a number of other connection types, of course. There's structs for representing structured data, right? Structs. And Rust also supports generic types as well. So here you see int point is a point where X and Y are integers, and then we have float point, which is same structure, but the values are floating point numbers, and we're using that generic T type in the struct definition there. Besides that, Rust also has enumerations that can also hold data, right? Like in this case, the key press variant of the event enum holds the key code of the key that was actually pressed, right? And these enums are used for 2 types in the Rust standard library that are used extensively in Rust, and you'll be using them extensively when you're writing Rust code. So they're worth being mentioned here real quick. One of them is the result type, which is used for operations that can fail, right? So Rust doesn't have exceptions that can be thrown, and you would typically use the result type instead. In this example, we have a try function that returns a result. And result is generic over the types of the success and the error cases, or the types of the values you're passing in the success and error cases. And here we are using a U16 number, so a 16-bit unsigned number for the success case, and a custom error struct for the error case. And then if the try function returns, and the try function returns a result then, right? Like maybe it performs a database operation or so, that could go wrong, right? Like maybe you get the Like you get the result of the operation, or maybe you get an error because database was down or something. And then when calling the function, we can use Rust match statement to handle the two possible scenarios, right? The case where things work fine and we receive the U16, as well as the error case. And here in this example, we don't care, so we just use underscore, which means we don't match it to a variable and we ignore it. Similar to the result type is the option type, which is used to represent the presence or the absence of a value, right? This is a bit similar to nullable values in language like Java. It's just a bit more expressive. So in this function, in this example, we have a function that returns an option of U16, right? And then when we call the function, we can use a match statement again to handle the two cases. So either we get some U16 or we get no value, right? Like none. So now that we've seen the basic language features and some types, I'd like to address the elephant in the room when talking about Rust. And I'm sure most or many of you have already heard of the dreaded borrow checker. It's a bit of a complex topic, and everyone who comes to Rust fresh is scared of it. And I would admit that that's at least partly justified also. And the point is Rust does not use garbage collection, right, for memory management, like language like Java, C# or so, or like .NET that we talked about before. And it also doesn't require developers to do their own it also doesn't require developers to do their own management like you would have to do in C or C++, right? Instead, it does compile time memory management in a way, right? So essentially for every variable, Rust tracks ownership, right? And binds the ownership to a particular scope. And then it knows when the variable goes out of that scope, and then it's safe to release it from memory, right? And then at compile time, Rust can automatically add in all the memory management for you, right? It knows sort of when the variable goes out of scope, so it can free the respective memory because of the fundamental rules in the language. And the borrow checker is one part of this whole thing, but probably the most infamous one, right? We will not go into a lot of detail here, but I want to show a brief example of the concept. So here the variable Ferris is a string that's defined in the scope of the main function, right? And then we pass the variable Ferris into the uppercase function and assign the result of that invocation to a new variable big Ferris, right? Which is Ferris but uppercase. And by passing Ferris into the uppercase function, we move ownership of the variable into that function, right? So the variable is not owned by the scope of the main function, but by the scope of the uppercase function anymore, right? And then Rust knows that at the end of the scope of the uppercase function, the variable can be freed, right? And yet, after having passed the variable into that other function, right, we're using it in the following line in the print line call, right? And that doesn't work because the variable has been freed at the end of the scope of the uppercase function already, and we get a compiler error. And again, you see the error is pretty well written and makes it clear what the problem is, although admittedly this will be very confusing when you're new to Rust, right? In this case, a simple fix for the error would be to simply pass the variable as a read-only reference so that ownership is not moved into the uppercase function, but still in uppercase, sort of you can use the variable, and this example will compile fine. As I said, though, it's a bit of a complex topic, and in particular also because many people that come to Rust from garbage collected languages, right, aren't even sort of familiar with the concept of memory management, right? So although you don't have to do it yourself here, sort of you don't necessarily understand what's even happening and why this is all necessary, right? Because you never cared, right? Like myself, when I came from Ruby and JavaScript and so on before. Like you learn it in university, but then you forget it because you rarely need it unless you do C, right? So, I mean, for now, I would say just know that Rust does compile time memory management, and that's one of the reasons why it's so fast, right? And if you learn Rust, then you will be struggling with this a bit, but it's also like you'll overcome it over, I don't know, like few days, few weeks or so. It's not a few years of studying sort of the basics of computer science again. So finally, to complete the intro to Rust itself, a brief look at developer tooling. First, there's RustUp, which is used to install Rust and update Rust itself. You can install different versions of Rust with it, as well as install like optional components of the toolchain, right? So that's pretty convenient. For managing dependencies in Rust, there's Cargo, which is Rust package managers. Dependencies are specified in a file called cargo.toml. It's similar to YAML. So if you just say dependency so and so, version so and so, and then Cargo installs these dependencies and also maintains a log file to ensure you're always using the exact same versions everywhere, right? That's something like log files are pretty common now in other languages as well. Cargo is also used to create new projects, to build projects, to run tests, and so on, right? So that's really sort of the main thing you use when working with a Rust project. You never really call the compiler yourself. So obviously Cargo build and Cargo test will like run the compiler as well, but you don't really do that yourself. So that's the very brief overview of the language itself. Like I said, probably a bit more than 5 minutes, but I wanted to talk about using Rust on the web, right? To build web applications, web backends. So what's the situation with Rust on the web? Is Rust web yet? And areweb.org answers the question with a clear yes, right? It's ready for the web and it's fast. So that's good news. And it's really the fact that, all of the aspects that you need to have covered when building web applications with a language are sort of covered in Rust, right? First of all, there's Tokyo, which is an asynchronous runtime. To provide some context, Rust separates the asynchronous syntax and language features from the runtime, right? In most languages, the runtime would be built in. In Rust, that's different. While there are other options besides Tokyo, though, Tokyo establishes as kind of the standard in the ecosystem. And it's also indeed pretty good, although you don't really directly interface with it. But Tokyo is the foundation for network applications, really, and used by most of the frameworks and similar libraries sort of that build on top of it. So it's kind of the main building block for using Rust on the web. So Tokyo is kind of the foundation, and then on top of that you have the web frameworks, right? There are quite a few mature options, all well maintained. The two most popular ones are probably Axum and ActX Web, which does not actually use Tokyo, but you don't have to care because it's under the hood anyway, right? You don't see Tokyo in Axum really neither. And without going into details here again, so we can state that sort of all of the lower level stuff you need when writing web backends like HTTP 1, 2, 3, WebSockets, TLS, and so on, that's all covered in Axum and ActX Web and other frameworks as well. So there's no thing holding you back writing whatever application in Rust really. And then kind of below or maybe next to the web frameworks, you have data stores, right? Again, like mature and well-maintained drivers exist for all of the relevant stores like MySQL, Postgres, Redis, and others. There's a couple of ORMs, like object relational mappers, if you want to use one. And then there's even a number of data stores that are written in Rust, right? Because Rust is an obvious choice for these cases. Clearly, like you have SurrealDB, a search thing. Tick, I think, is similar to Redis. The Neon, I think, is kind of a Postgres backend that can like move things around in the cloud and so on. And I think lots of fork stores and so on. And then there's a number of other things you need when writing a web app, like serialization, deserialization into and from a number of formats, which is handled by Serde, which is awesome. Everybody in the Rust community likes the Serde crate. There's implementations of various messaging formats. There's crates for internationalization as well as templating, and essentially everything else you need, right? So overall, as web.org said, is ready for the web. And we at MainMaker believe that sort of building web apps with Rust will actually take off in the next month and years probably. And it's even relatively easy, right? So let's look at a small Express app as an example here. So here you see we run a server on port 3000, and then we respond to GET requests to the root path with a static string. The equivalent in Rust is actually pretty similar. We import some types, we define the main function, which we need to mark with Tokyo's main attribute to allow it to execute asynchronously. Although that's kind of the only direct interaction with Tokyo you typically have. We then create an application and route GET requests to the root path to a hello world function. So essentially same thing that we do in Express on the left. And then the rest of the code in the main function essentially just starts up the server and binds it to port 3000 on localhost. The hello world function itself simply returns a static string like in the Express example. So that's Rust and the state of web development in Rust in a nutshell. Right? So now you might ask, why? Right? Like, why do I even care? Why should you care when you're happily using Ruby, Java, Elixir, TypeScript, Go, .NET, whatever you're using, right? Adopting sort of something new and switching to a different ecosystem, community, and so on cause friction, and there must be a reason, right? What could actually motivate a decision to adopt Rust and use something new instead of just sticking with the old, which we all like to do, obviously. So to explain why you might indeed decide to Rust why you might indeed decide for Rust in some scenarios, I want to go back to our previous example, right? So seemingly there isn't a big difference between the two implementations, right? Just by looking at the code. One implementation is typed while the other is not typed. Although you could use TypeScript for Express and then they both would be typed. Obviously Rust is a bit longer, right? It has a bit more sort of ceremony. But overall, it's not so different, right? However, when you run these, we see that they're actually quite different. So if we run a simple load test here, right, that sends requests for 10 seconds using 128 simultaneous collections, then we see that Express manages to complete around 13,000 requests, right? And the same load test manages to complete almost 130,000 requests against the Rust server, right? So obviously, you can do the calculation. It's a 10. It's a factor 10 difference, right? So we get 10 times the number of requests sort of with the same load test than we get from Express, and it's no surprise really, right? Everybody knows Rust is extremely fast, but I think one important difference is that Rust is not faster on average, but performance is also more consistent, right? The problem with all garbage collected languages, like in this case JavaScript, is that performance charts look something like this, right? You have spikes which occur sort of in intervals whenever garbage collection runs, right? And the VM essentially must hold everything to free up unused memory, right? In some languages, sort of you can tweak the VM and sort of make the spikes look different, like less often or not as high or higher, but more often, whatever, right? But in essence, sort of you can't get rid of them, right? You always need to run garbage collection at some point because you don't have unlimited memory. So the problem is you cannot really achieve consistent and reliable performance all of the time, right? So if you're P95 or so, it's always going to be different from your average performance. For a language like Rust, right, that does not have garbage collection, the performance chart looks like this, right? It would probably be like be significantly lower as well because it's faster, right? But the point is, you don't have these spikes, right? It's a flat line, and you get consistent performance all of the time, right? As we saw before, Rust knows when variables go out of scope, sort of, and then it can free it. So sort of memory is like constantly allocated and then freed sort of as the program executes, right? And before Rust came along, the only other alternative to get this kind of high and steady performance were C and C++, right? Of course, there were other languages in theory as well, but like only these two were really relevant, right? The problem with C and C++ though is using them is like juggling chainsaws, right? And that's not something that I say, but something that Linus Torvalds says, who has, I don't know, probably written millions and millions of lines of C code. So C and C++ are obviously very powerful, but also really dangerous, right? It's like there's a lot of pitfalls everywhere, so you can really only use them when you're are an expert or you have an expert team, right? So in essence, sort of no teams that operate in contexts where C and C++ aren't widely used anyway, like the web, could really dare to use them, right? It's just too dangerous. It would just be too easy to shoot yourself in the foot, sort of to an extent where the whole foot or entire leg falls off afterwards, right? And that meant that a certain level of performance and efficiency for some use cases has been out of reach for those teams and for building web apps entirely, right? Until Rust then came along, which allows us to achieve the same performance with more efficiency and without the risk of shooting ourselves in the foot massively, right? And the performance and efficiency sort of aren't only relevant so web servers could deliver responses fast, but having a server that only needs 1/10 of the time to respond to a request also means that we can respond to the same number of requests with 1/10 of the servers, right? Which of course is a bit of a simplification, but I guess you get the point. And something I personally experienced when starting to use Rust, coming from Ruby and JavaScript and these languages before, is sort of you develop a bit of a strange expectation or idea of what computers can do, right? So you get used to like relatively slowly executing programs, and then sort of once you run something in Rust, so you're really surprised. Like, well, I didn't expect this to be as fast on my like 15-year-old notebook or whatever, right? Yeah, so being able to do the same thing with 1/10 of the servers also means that you have 1/10 of the hosting cost, of course, right? And that can actually make a substantial difference. So cloud hosting is great in many ways, but it's not cheap, right? And being able to cut off 90% of your AWS bill or whatever can make the difference of a few hundreds of thousands of euro per month, even if you're not a huge company, right? And these numbers are real. Here's a bit of a random quote from Reddit, which is admittedly not a scientific source, but sort of the numbers are representative, right? So they say they can fit 4 Rust services on a node that fit 1 Python service before, and each of the Rust services achieves 14 times the throughput compared to Python, right? So that's a pretty big deal, obviously. And Rust performance and efficiency result in real cost savings, right? And we're not only saving money, but of course, only using 1/10 of the servers also means we're using 1/10 of the energy and the resources, right? And I think that's something that is worth mentioning and something that everyone should maybe think about sometimes, right? Like running data centers and so on renewables is good, right? But the greenest energy is the energy you don't use, obviously, right? It would be ridiculous not to claim that Rust is going to solve climate change and so on, right? But I think it's worth thinking about these things as well, and thinking about sort of that whatever we do, the software that we write, is eventually going to use electricity. Servers need to uh, uh, um, servers need to be produced and so on, right? And that's sort of, if you can use less of all that or get more value out of sort of the same resource input, then that's certainly something that we all should be trying to do, I think. So the performance and efficiency that Rust comes with is one good reason to use it, right? In cases where that matters, obviously. But there's another reason as well that's maybe not as obvious and therefore typically overlooked a bit when talking about Rust. And that's the reliability and the maintainability gains that you get from Rust's strong typing system. In the early days of my career in web development, sort of there was the release of Ruby on Rails, right? Before that, we had things like JSP and J2EE even, and so on. And then Rails and Ruby meant a significant step up in terms of expressiveness and just how easy it was to write web apps, right? You had code like this, which was obviously so much better than Java classes and XML configuration files and so on, right? And it's still pretty great, right? It's expressive and it lets you reach your goal fast. However, there's a problem with that, right? In this example here, I can see the user's attribute, but there are no rules there, what values are allowed and what combination, for example, right? So for example, you might think that if active is true, activation days must probably be set as well. If active is false, I guess activation date must be nil, right, which is Ruby's null. I can look at the activate method sort of to validate these assumptions, but these things are not really encoded anywhere, right? And the function signature also doesn't tell me what the argument is exactly, right? Whether it's a date, timestamp, a stringified date, maybe. And looking at the usage of the method, I don't know whether the method potentially throws an error, right? If I wanted to rename the class or the method or anything, the best I can do is run search replace over the entire code base and then sort of hope for my test suite sort of to cover all invocations in case I miss an occurrence. And these all might seem like made-up problems that aren't really so relevant in reality. And maybe you don't even want to let go of your sort of love of programming like this, like DHH is the inventor of Rails, sort of who seems to consider typing a chore, right? That takes the joy out of programming somehow. And to some extent, I can even relate to the sentiment, right? But the problem in reality is sort of the longer you work on your app and the larger the code base becomes and the larger the team working on the code base becomes, the more you start to feel the impact and those of the problems mentioned before, right? Sort of the cost you're paying, the price you're paying for that kind of freedom, right? You don't have a small tight-knit team anymore where everyone understands sort of the entire application and is aware of all of these concepts and rules that are somehow present in the code but not encoded in any interfaces or data structures, right? Instead, sort of you need to read through classes and methods and test cases to understand all of those rules, right? And the bigger the code base becomes and the bigger the team becomes, the more unrealistic that task becomes and the harder it becomes in particular for new joiners to join and work on the code base, right? So you end up with what I call like a CSS scenario, right? Nobody dares to change everything, so you just add stuff, right? Like rather add a new method doing like a similar thing but slightly different than making these the existing ones sort of like configurable via parameters. So, and that's obviously a maintenance nightmare, right? And yeah, that kind of problem has also sort of been widely recognized throughout the industry and led to a number of efforts to address it, right? So first of all, TypeScript, of course, which was built for that reason, essentially, right? In Ruby, there's Sorbet, there's also RBS, then there's Gleam, which is similar to Elixir, runs on the Beam as well. There's type specs in Elixir. There's no types in PHP. I think Facebook Hack has some types as well. There's type hints in Python. There's MyPy and more, right? Like most languages have something like that going on, right? And those improve things. Like looking at the previous example with added types, this is a bit better, right? We know what. So we now know exactly what things are and don't have to sort of rely on a test case, for example, that checks the correct thing happens when you pass in like a string into the activate method or something. But it's still pretty limited, right? I don't know when active's true activation date must be set as well and can't be set otherwise and so on, as I said before. I don't know whether the activate method might change the argument. I don't know, it can be a relevant question in some cases. I don't know whether the method throws, perhaps, right? So this is a step forward, but it's really kind of a hack, really, right? Because instead of starting from the goal and thinking sort of about what you'd ideally like to have, sort of all of these typing approaches need to start from the status quo sort of the respective languages and then provide a path into the future, which is the point, right? Nobody wants to rewrite their JavaScript code base, their Ruby code base and so on. So they do something that lets you progressively transition to types while maintaining backwards compatibility. On the other side, Rust obviously does not have that history, right? So let's look at the same example as before, but in Rust. So first of all, we see this is obviously more code, right? We're expressing more things, so we need more lines and characters to do that. But there's also a whole bunch of benefits here, right? We clearly define what inactive and active users look like, in this case in enum, right? So that inactive users don't even have the properties of active users, right? I know exactly what the argument to the activate method is. Even the time zone is in the interface. I also know that the argument can be changed by the method because it's not marked mutable. And the function signature makes clear that the function can throw or can like result in an error because we use Rust result type here. So obviously this is a rather simple example, but I think it illustrates the point, right? In a code base like this, it's much easier sort of to make changes confidently, right? Because you have all these interfaces and so on that prevent you from making mistakes that would only show up as bugs in production. Yeah, so that's what I believe is the second reason to consider Rust in many cases. And maybe even the one that's more relevant in many cases than performance and efficiency even. I'm speeding up a bit because I don't think I have too much time left. So now having the what and the why established, let's have a look at the how and where to adopt Rust in web development, right? I want to talk about use cases as well as I want to talk about use cases as well as cases where Rust might actually not be a great choice, and then also adoption path. It's still a bit of an unexplored area. It's like still early stage, so this is somewhat based on what we see happening in the industry, and also some partly based on our expectations for the future of the sector. So first of all, we've already established that Rust gives you reliability, maintainability, efficiency, and performance, right? So use cases for Rust are obviously areas where these four are relevant, right? Of course, you could say like those four are always relevant, and you'd be right in a way, but of course, you also don't really get these benefits for free, right? There's a cost associated with using Rust. If you compare Rust to alternative, roughly similar technologies, like for example Go, although Go has garbage collection, obviously, of course you get more value, right? You get a bit better performance, you get Rust superior type system and so on. And you get more stable performance because there's no garbage collection, right? The additional value comes at a cost, though, right? You will invest more effort into building a system with Rust than you will with Go, at least initially, right? There's no lying about that there. So when talking about use cases for us, the question typically is sort of, are you willing to make that additional investment to get those extra 10, 20, whatever % of value, right? And for many cases, the answer might be no, but for some cases, the answer will be clear yes, right? So things like your core business system, sort of, that implements the core business logic of your server and of your service. Also, right, there you care about long-term stability. You don't really have tolerance for bugs in production and so on. On the other hand, sort of the HTTP API that's on top of that, maybe you want to have additional flexibility and so on. Maybe Rails is better for that, right? For any financial system, obviously, you generally have little tolerance for bugs and want them to be really stable. And also for a lot of finance systems, sort of the faster you run, the more money you make because you can trade faster or something. Anything that's high throughput and must be high performance is an obvious use case, right? So for example, think about you have an HTTP API implemented microservice, you have sort of a facade proxy in front of that. That's a really good use case for us, right? You don't want to have like these garbage collection spikes in your performance chart and so on. And you want it to be super stable because otherwise you take your whole system down. And of course, for anything that you're running at large scale, right, you'll see large savings in energy and money when switching to Rust. So that's a clear use case as well. So adoption path and architectures. How do you start, right? If you have sort of established you want to use Rust for one of these use cases potentially, how do you start then, right? How do you adopt the technology and what are the architectural and also perhaps organizational considerations? And the easiest case, of course, is you're starting from scratch, right? As we saw before, Rust is a viable choice and the ecosystem is sort of ready to go, right? The thing to keep in mind, though, when using Rust is it is not your friend when you don't really understand the domain yet and you're still exploring, right? While technologies like Rails are so awesome for that because sort of they get you like going fast and they let you sort of reach the first prototype faster. So Rust is a bit different. Sort of Rust is maybe a bit harder in the beginning, and then sort of you see the benefit sort of at later stages more, right? So think about a case where you're sort of still experimenting, right? Then it's a bit hard with Rust because in order to compile, sort of your entire code base needs to be consistent, right? So for example, changing a struct to see whether that particular change sort of works in one particular endpoint of your server, sort of you can't do, right? You now need to change all of the other usages of the struct as well before you can see how it behaves in that one particular endpoint, right? So the clearer your idea of the domain as well as the architecture are, the easier it's going to go with Rust, and sort of the less you will be struggling. Another thing to keep in mind is there's no Rust on Rails, right? There's no full-featured batteries included framework. Sometimes you might care, sometimes you might not care so much, but if you need sort of a big framework, you will at least be partly sort of assembling that yourself based on the available building blocks, right? A case where you don't really care so much about a macro framework is, of course, where you're just building individual microservices, right? In these cases, sort of many of the concerns of a full-featured macro frameworks are not relevant anyway because sort of limited scope, you don't need the functionality, right? I'd say moving sort of or re-implementing sort of individual microservices in Rust is sort of the typical adoption path, and it's also sort of low risk, right? It's limited scope. You're not committing like a big team to building a big thing, but over time, sort of you can then migrate more and more microservices or sort of extend that first microservice as well. Another easy adoption path, let's maybe skip over that, is building native extensions. So most languages sort of have some sort of mechanism, like Ruby, Elixir, JavaScript, sort of all of them sort of allow building native extensions. Previously, you had to use C or C++, which you couldn't, as we saw before. So now with Rust, you can do that, right? So finally, one quick thought about sort of the future of Rust in web development, right? As I said, while the ecosystem is mature enough to make Rust a reasonable choice already, it's still relatively early stage, right? As I mentioned before, you're already getting more value out of Rust compared to roughly similar technologies like Go due to superior efficiency, performance, as well as stability and maintainability. But there's also additional effort required as well, right? The goal is to bring the effort down, right? To bring it down to a level that's similar to other technologies, so that you end up with similar or the same effort but additional value, so that the decision for us becomes much more obvious and Rust becomes a viable choice for even more use cases, right? I just talked to the maintainer of Actix Web recently, and he said that specifically that is the goal, right? They want to make it sort of as easy or similarly easy to writing a web app with Express in JavaScript, right? And then sort of for the same effort, sort of you get much more value when using Rust. And that combined with improvements in the language itself, as well as the fact that everybody loves Rust already, really means there's a bright future ahead, right? So we really believe that there's a future in web development where we all have access to a technology that allows us to reach like new levels of efficiency, stability, and maintainability without giving up on developer experience and productivity, right? While giving up on the challenges and frustrations that many teams face regarding long-term maintainability of systems built with technologies that had the goal to focus on developer experience in the first place, like Rails, for example, right? If you're now intrigued and want to learn more about Rust, you should come to Eurorust in Brussels in October. It's our 2-day conference about all things Rust. There's also going to be workshops and so on, and closing party Friday night. I put some stickers there for anyone who wants one. If you can't wait until October, you can also join our remote workshop in July. It's like 3 afternoons. Teaches everything you need to know to build web apps with Exum in this case. And with that, I'm closing 2 minutes over. Thanks.